Here are our solutions to homework set number 1 for ECE 376. This homework is just kind of background on a PIC processor. With a PIC, you can drive 25 milliamps, you can measure voltage to 4.88 millivolts, you can measure time to 100 nanoseconds. What does that mean? Well, the first problem is if you connect an 8-ohm speaker to your PIC. 8-ohm speaker, of course, is 8 ohms. At 5 volts, that's 625 milliamps. A PIC cannot drive an 8-ohm speaker directly. If you do this, you'll burn out the I/O pins. Instead, what you need to do is you need to reduce the current. Add resistors in series to limit the current to 25 milliamps. Well, 5 volts at 25 milliamps is 200 ohms, so I need a minimum of 200 ohms connected to the PIC. With that, I can do a 192 ohm resistor, which don't exist, so just add 200 ohms resistance in series with the speaker. That limits the current to less than 25 milliamps, and you can drive a speaker. Won't be as so loud that you can annoy your friends and neighbors, but plenty loud to hear. Problem 2. If I can only measure, or if I have a voltage divider, let's go back over here, like so, and I can measure voltage to 4.88 millivolts, how much can R2 change and still detect that change? Well, first what I want to do is if R2 is 800 ohms, find V1. And that's by voltage division. V1 is R2 over R1 plus R2. Plug in 800 ohms, 2.2222 volts. Now add 4.88 millivolts to it. This is how much the voltage has to change for the PIC to see it. If V1 becomes 2.227 volts, that plus 4.88 millivolts, I can see that. How much does R2 have to change? Well, by voltage division, I have this. Now calculate R2, so this is 2.227. Solving backwards, R2 is the voltage over 5 minus voltage. Do a little bit of algebra, you can get that. R2 needs to be 803 ohms. The difference is the resolution. So went from 800 to 803. R2 has to change by 3.16 ohms for the PIC to detect it. Or in other words, I can measure 800 ohms with a resolution of 3 ohms. That's what 4.88 millivolts means. If I replace R2 with a thermistor, like the ones in your lab kit, the resistance versus temperature follows roughly this equation. How much does temperature have to change? Well, at 800 ohms, if I solve, the temperature is 30.126 degrees Celsius. If R2 is 803 ohms, it is 30.06 degrees Celsius. The difference is my resolution. So the PIC could measure temperature to about 0.09 degrees Celsius, which is not bad. That's what 4.88 millivolts means. Problem 4 is I can measure time to 100 nanoseconds. What is 100 nanoseconds? Well, if you take the world's fastest slapshot, that was 110 miles an hour, or 46 meters per second, the time it takes to travel from midcourt is 27 meters over 46.98 meters per second, gives you 0.57 seconds. If I add 100 nanoseconds to it, let's see, one of these numbers changes. 1, 2, 3, 4, 5, 6, 7. This number changed. Went up by 1. That's the smallest time change the PIC can see, 100 nanoseconds. If I go back and calculate the velocity, if this is the time, the puck is now traveling at 46.9799918 meters per second. The difference between those two is 0.000008 meters per second. So with the PIC, I can measure speed to 0.000008 meters per second, which is pretty darn impressive. Basically, if you measure time to 100 nanoseconds, you can measure things like speed really, really accurately. Another problem. Suppose I had a 555 timer. What this does is the capacitor right here charges, discharges, charges, discharges, outputting a square wave. The period of the square wave follows some equation, this equation right here. If you plug in the nominal resistances, the period is 396.4 microseconds. And whenever the period is the frequency. So this will be a 2.5 kilohertz square wave. If the frequency changed, The smallest change I can see is 100 nanoseconds on the period. Add 100 nanoseconds to the period, so instead of being 0.48, that becomes 0.58. Now calculate the frequency. The difference in frequency is your resolution. With a PIC, I could detect a change of frequency of 0.63 Hertz at 2522 Hertz. Again, pretty impressive. Problem 8 is if R2 was a resistor, I could measure the resistance. At 800 ohms, I have this period, 365.48. If the period changes by 100 nanoseconds, again the smallest time change I can see, the resistance would have to change from 800 to 800.3 ohms. Again, plug in time, I know R1, I know C, solve for R2. You get R2 is 800.3. So the resolution is 0.3 ohms. If I made C something bigger, like 22 microfarads, I could measure the resistance to 0.003 ohms. Again, if I can convert something to time, I can measure really accurately. And measuring 800 ohms with a resolution of 0.003 is really impressive. The final problem is suppose R2 is a thermistor. If I can go from 800 to 803 ohms, that's the smallest I can see, smallest change in resistance I can see. The corresponding temperatures go from 30.16 to 30.15 degrees Celsius. The difference in temperature is my resolution. So the difference is, let's see, 0.009 degrees Celsius. Made the capacitor bigger, I'd actually have a resolution of 0.00009 degrees Celsius. Really impressive. So that's homework set number 1. Just kind of a background, how much can a PIC drive? You need at least 200 ohms at the output. I can measure voltage to 4.8 millivolts. What's that mean in terms of resolution on resistance and temperature? I can measure time to 100 nanoseconds, so I can measure speed to 0.0000008 meters per second. I can measure the second place finisher. If you finish 1.29 microns behind the first place person, I can see it. That's less than the width of a human hair, less than the size of a bacterium. I can measure frequency to 0.6 Hertz, or resistance to 0.3 ohms, or temperature to 0.009 degrees Celsius. Pretty impressive. So anyway, that's homework set number 1. The processor we're using isn't the world's most powerful, but it's still pretty darn impressive. So homework set number 1 for ECE 376. If I could end this. There we go.